Glen Cove, New York with her husband and daughter, where she continues to enjoy tutoring students of all ages and backgrounds. Siobhan's talk today is entitled Solving the I Hate Math Problem, Insights into Overcoming Common Obstacles. Welcome to Siobhan.
In the name of the Father, and the Son, and of the Holy Spirit, amen. Directly beseech thee, O Lord, all our actions, by thy holy inspiration, and carry them on by thy gracious assistance, that every prayer and word and work of ours may begin from thee, and by thee be happily ended. Amen. I offer this quote from Johannes Kepler, who lived from 1571 to 1630. Geometry is one and eternal shining in the mind of God. That sharing it, according to men, is one of the reasons that man is the image of God. Good afternoon, and thank you for inviting me to speak at your impressive and valuable conference. As some of you know, I'm a mathematics teacher who left a typical classroom in 1999 to start a tutoring company and work in an alternative school where students who had been suspended from the high school were sent to learn. I was their math teacher in a one-on-one situation. During that time, I endeavored to tutor students of all ages and backgrounds in a private undertaking as well. It was one of the best decisions I ever made to leave the typical classroom for numerous reasons. First, being that through a homeschooling family of 11, 5 of whom I tutored, I met my now husband, and by God's blessing, we now have a beautiful daughter. Second, I have learned more as a teacher about learning and teaching from the mostly one-on-one contact I have enjoyed with my students than I think I ever would have had I remained in the classroom. It is through these experiences I come to you armed with the I Hate Math solutions, where I hope to expose 5 common pitfalls which ensnare students and parents, and hopefully offer some ideas about ways we may approach these challenges. First, though, I would like to ask the audience a question. Why do we learn mathematics? Would anyone care to assert a reason as to why we learn mathematics? Yes.
It explains our world.
It explains our world. Very true. Yep. Anyone else?
And necessary to manage your finances.
Excellent. Yep. Definitely necessary to manage your finances. I agree with that.
Plus, I love purity.
The purity of it. Okay. I enjoy that too. I'm glad you mentioned that. Yes.
Helps you to think generally and generalizations about place problems and solutions.
Okay. Very good. Yes. It helps you think generally and make generalizations about problems and situations. That's very true. Thank you. Anybody else want to get out of high school? No. That is actually buy groceries. Yes, to manage your finances. Yep. So, other possible answers: understand concepts of quantity, get through life, to get the best return on your taxes, to understand our economy and the freedom it brings, and to learn how to think. In 1942, Dorothy Sayers, a colleague of C.S. Lewis, wrote an essay entitled The Lost Tools of Learning, where she suggests that in this day and age, we teach our children everything but how to learn. She addresses the proper training of the mind by exposing 3 stages of learning, which I know the last speaker spoke a little bit about too, and bear with me while I also speak about them a little bit. She exposes 3 stages of learning called the trivium. Ms. Sayers discusses how they relate to a student's age and maturity level. The first stage is grammar, whereby a student is learning the accurate meanings of things, words, symbols, definitions. While she says it may not be clear when the second level is appropriate, the dialectic or logic, it should be apparent when the student is prone to interminable argument, and therefore the tools of formal logic should be taught, all within the subject matter which we are using, and math really lends itself to this. At the final stage of the trivium, the rhetoric stage, the child has mastered the language and the definitions. He can make original, cogent argument and put forth reasoned and synthesized thoughts. Here's what Ms. Sayers says about mathematics at the rhetoric, the 3rd stage. Mathematics, algebra, geometry, and the more advanced kinds of arithmetic now enter into the syllabus and take its place at what it really is, not a separate subject, but a subdepartment of logic. It is neither more nor less than the rule of the syllogism in its particular application to number and measurement, and should be taught as such, instead of being for some a dark mystery, and for others a special revelation, neither illuminating nor illuminated by any other part of knowledge. And for anyone who is not aware of what a syllogism is basically deductive reasoning. For example, you start with the premise, all virtues are good. You make an assertion, kindness is virtue, and then you draw a conclusion, therefore kindness is good. So in mathematics, that is the second level, basically, of the trivium. And she talks about getting to the third level, the rhetoric, where then you can use those facts to assert your own cogent thoughts. So we are all here hoping to solve the I hate math problem. We may not be able to make someone like mathematics, but we can do a lot to help students to enjoy the beauty of it. One has a firm grasp on how to learn mathematics. Yes. We can steer them towards loving the ability to think. It is important to keep in mind as we go forward why we teach mathematics, and especially why we teach higher level mathematics. I wish I had a quarter for every student who has asked me, when am I ever going to need the quadratic equation? And I say, you are learning how to learn. Of course, I think they think to get out of high school is more of the answer to that. As a mathematics teacher, I encounter every different kind of reaction and attitude towards mathematics, from ecstasy to sheer loathing, but it is rare that students are indifferent towards it. I can recall during my own learning the times when I would ask my father for help, specifically with math homework. Before too long, he was inevitably impatient with me, like how people sometimes gradually work up to a yell when speaking to someone who doesn't understand the language. Well, in a way, mathematics is a language of its own. It has its own set of symbols, subjects, and verbs. Galileo Galilei is noted as saying that mathematics is the language in which God wrote the universe. So, the answer to the student who wants to know when he will ever use the quadratic equation might be better if I offered to him that mathematics is a language, like any other, whereby one can reason and think. I want us to think about why we teach math, so that as we instruct our children in the wonders of mathematics, we revisit these objectives. For some, the reason to get out of high school is the best they can come up with, and so it is no wonder they have a negative attitude towards math. So what happens along the way? When and where does a child decide that he strongly dislikes math? My 2-year-old daughter knows her numerals from 1 through 10, but what does that mean? She can look at a symbol for the number 5 and say 5. But at the age of 2, she really does not understand what 5 is. Most times when she is counting 5 things, she makes a mistake by either counting the same thing twice or just continuing. 6, 7, 8, 9, 10, 19, 23. You see that she does not yet connect the symbol, or what we call the numeral 5, with the ordinary amount of 5. Ordinary in the sense of being counted in order, like time. So, I'd like to talk about 5 common pitfalls. The first pitfall to which I'd like to draw our attention is that numbers, numerals, and symbols can confuse the daylights out of us. We understand them, we misunderstand them. They are the source of so much confusion in the minds and lives of children, and I dare say, adults. Consider for a moment the number 10. Is that what you were expecting me to write? No. Maybe so, but most would be thinking of the numeral 10. Why don't we use Roman numerals so much anymore? Well, they are not very user-friendly. We cannot add and subtract them with the ease we can the Hindu Arabic numerals. The symbols for the numerals we know as 0, 1, 2, 3 to 10 come to us from India through Arabia. Then they came to Europe and then here. These are known as Hindu Arabic symbols. They use the digits with which we are familiar. Does anyone know how these particular symbols came into use? Like, does anybody know why the numbers look as they do? Yes?
They come with the angles.
Yes, very good. Yes, so if I could just demonstrate. 1 has 1 angle right here. That is what the 1 looked like before. Now, a lot of times we've changed it to that, or even some people do that. But originally it just had 1 angle. 2 is 2 angles. You can see them here, 1, 2. 3 angles, 1, 2, 3. 4 looked like this. 1, 2, 3, 4. 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 7 had an extra, 1, 2, 3, 4, 5, 6, 7. 8, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Got kind of crazy. 1, 2, 3, 4, 5, 6, 7, 8, and I had one more tail. 9. Okay, and the number and what they represented 0 has no angles. So these were the numerals that came into, the common understanding, and they're very useful in that, well, I'll talk about why. So now think about the numeral 10. This is the numeral 10. The number 10 is the abstract idea of 10. You have 10 objects, but the numeral that we use is numeral 10. We're all familiar with it. The number 10 is just the amount of 10. At some point we want to show children how to represent that amount with numerals. So why 1 and a 0? We are trying to convey an idea of place value. For 10, we use this idea of holding a place, or counting in tens. We count from 1 to 9, all single digits. And then when we get to 10, we count that there are 2 digits, 1 and 0 next to each other. Back when we used an abacus, this was visually apparent since the beads could be counted out, and then we could hold the place for the bead on a different line, usually also of a different color. Unfortunately, we occasionally jump from a visual like the abacus to paper and symbols and expect the student to make that transition without time to internalize that jump. We might say to a student, just add a 0. So a student hears just add a 0, and in his head is thinking that, which is this. If you add a 0, you are not adding any quantity. When what we're really trying to say is hold a place with a 0, or annex a 0. When we say add, it has a different meaning. We want to be clear that we are annexing 0, or that once we count to 9, the tens place gets a mark, and we hold the 1 spot with a 0. A concrete example can do wonders to avoid simple confusion. I recall the days when I was learning how to tell time, long before the advent of digital clocks. At no time had anyone reviewed with me the idea of counting by 5s. So I would see the big hand pointing at the 2 and heard, "It's 10 after." And I can't tell you how confused I was. And it didn't help that this continued for quite some time until it became apparent somehow that these people are counting by 5. In this case, the symbols on the clock, numerals, familiar to me, but I was not familiar with the way in which they were being used. So imagine how students feel when we throw in something a little more advanced like Now, I don't know if you can all read that, I'm sorry. It basically says f of x when x squared is less than or equal to 0, or x plus 5 when x is greater than 0. Now, I've just used that as an example of a common thing that a student in maybe 8th or 9th grade might see, and if they're having trouble with symbols in general, this looks like total gobbledygook. So, we just want to be aware of this. My point here is that when a student does not understand a symbol, it can cause confusion and result in distaste for mathematics in the early stages of learning. In my examples, I have merely made reference to the digits of numerals. Imagine how the entire catalog of mathematical symbols can overwhelm students. Some students need more time to internalize that the symbol represents something else or tells him to perform a certain operation. He is stuck until the meaning of that symbol becomes part of his language, like using subjects and verbs together correctly when speaking. We sometimes take symbols for granted, and it would do us well to discover with our students each symbol as if it were new to us as well, and be careful not to confuse the student with incorrect vernacular like add a zero. I'm just going to erase this. A reality I'd like to address is that not everyone learns in the same way, which I know was also alluded to in previous talks, but I'm going to continue with it too. We do ourselves a disservice by attempting to educate everyone in the same way, since not everyone learns in the same way. I would also suggest that although some people may find it easy to learn a certain way, if information is presented to them in multiple ways, they will embrace a more thorough ability to synthesize and interpret information, and thus be more creative with information. Yes, I did say creative, and yes, I am talking about math. The essence of mathematics is freedom, said the mathematician George Cantor, who lived between 1845 and 1918. So our second pitfall is that we tend to educate in a cookie-cutter, one-size-fits-all fashion. Howard Gardner is attributed with enumerating these multiple intelligences, as he calls them, in a 1983 book called Frames of Mind. Interestingly, Gardner is self-described as cross-eyed, myopic, colorblind, and unable to recognize faces. He does wear very thick glasses. So it is no wonder that he, Gardner, is able to identify these different intelligences or ways in which people prefer to learn. Gardner holds a chair as Professor of Cognition and Education at Harvard Graduate School of Education. He originally enumerated 7 separate independent intelligences, though he now suggests there may be 8 or 9. Nonetheless, it is worth considering the ideas Gardner asserts. I will list them and speak briefly on each. So his intelligence types are, does it help if I write these on the board, or should I just speak them, or just speak? Okay. Linguistic, which involves words and language. Logical mathematical, which involves logic and numbers. Musical, music, sound, rhythm. Bodily kinesthetic, body movement and control. Spatial visual, images in space. Interpersonal, which regards other people's feelings. And intrapersonal, which is self-awareness. Merely due to time constraints, I am unable to give each of these a thorough exposition. However, I offer them here to acknowledge that people have a preferred learning style and natural strengths. Knowing this, we should strive to present information in more than one dimension. We should strive to identify our children's preferred learning style. This is not to say that a student may not be expected to perform to a certain standard, but as each of us is unique, we will do well to acknowledge that people learn differently. If you have a child who is having trouble learning from a book, you may take heart in the knowledge that you may not be tapping this person's learning preference. One student I remember very well was strongly auditory. If he was allowed to read his assignments aloud and think aloud, he was an A student. Without that combination, however, he was barely a C student, and that's even if he just showed up to class. It was fascinating to hear him reading a mathematics question and thinking through the entire solution aloud before ever touching pencil to paper. Of course, he still had to write out his answers on paper, but as long as he could hear the question aloud, and as long as he was given the freedom to speak aloud, he reasoned his way through complex geometry proofs and other advanced mathematical challenges with practical ease. This young man had been expelled from high school and was placed in the alternative school where I taught. He is now a college graduate and productive with a job. I do not doubt that much of his frustration in school can be attributed to 10 years of the challenge of being forced to learn in a way that really didn't suit him. Once we determined that he was quite able to learn a certain way, he excelled. One of the beautiful benefits of schooling our own children is that we can take the time to get to know what learning style is preferred by our children and offer instruction which offers the highest likelihood of success. So what does this mean we should do? Well, since we homeschool, we have options and we make instructional choices and decisions about our approach to mathematics. Fine, maybe we can choose a textbook. That's probably a given. But what other mathematical experiences are we offering our children? I would suggest that we use more than one source for our math instruction. There are thousands of free videos available online from Khan Academy, that's one example of a place where you can find free instruction. A student can watch and rewatch to his satisfaction. Some extended sources could be from an organization called Math Counts. While Math Counts is intended for some level of competition, it also offers free workbooks online or hard copy if you enter a team, which is also a lot of fun. It was through Math Counts that I first had my students design golf courses to specific criteria. So many par 3s, 4s, 5s with a range of yardage on a given plot of land with a certain number of sand traps and water hazards, all using angles. And don't forget, the 9th and the 18th holes have to terminate at the clubhouse. The students got busy collecting old golf maps from relatives so they could see what a typical course looks like. They cut out shapes which satisfied the given conditions and set to work maneuvering them within the given plot of land. We eventually made large-scale models using paper mache and painted them for color. A third pitfall, starting with a definition, just to show you why this is a bad idea, let me give you a definition of the word definition, as taken from the online Merriam-Webster dictionary. Definition: a statement expressing the essential nature of something. A statement of the meaning of a word or a group of, or a sign or a symbol. So to further make my point, I'll mention the definition of a common concept and see how many of us know what I'm talking about. Here's the definition. A set of points equidistant from a given or known circle. Does anybody know what that is? Yes. Circle. Circle, exactly, yes. So if you guess circle, you are correct. But raise your hand if you think you should begin a lesson with that. Okay. I'm glad you agree. A more interesting way to approach definitions is to give a student some experience with a concept before generalizing it in a definition. One way in which to accomplish this particular definition, while also keeping the multiple intelligences in mind, might be to give a student a long piece of string and a piece of chalk. Go outside and mark a small X on the driveway. With the help of a sibling holding one end of the string on the X, the student wraps the string around the chalk. Let me get it straight. And uses it. Okay, so you have a piece of chalk, a string. Mark an X. Put the string on the X and walk around the circle. Okay. This part doesn't look very circular, does it? What he's drawing is that set of points equidistant from a given point. You can measure the length around the circle, which we call circumference, and the length across the circle, which we call diameter, and divide them. No matter how big or how small your circle, when you measure accurately and divide circumference by diameter, you will get a number close to 3. This is pi. See how much more fun that was? Now we know the circle, the radius, diameter, circumference, and I even threw in pi. Or you could give a definition. A lot of people do start with a definition. Pi is 3.14, 159, etc. There's no relevance to that. So by drawing it, by measuring it, by dividing circumference and diameter, we understand what is pi. So imagine telling a student a squared plus b squared equals c squared. We've all heard that. Pythagorean theorem. Or we can use a piece of graph paper to draw a right triangle with sides of lengths 3, 4, and 5. Now make squares of sides 3, 4, and 5. For example, we draw a triangle, and this might be length 3, this might be length 4, and this might be length 5. Now on a piece of graph paper, if you count 4 boxes and 3 boxes, and then connect that, that length will be 5. You draw a square with that length. That's 4 here. This is the same length 4 here. This is a 4 by 4 square. You draw a square of length 3, and you draw a square using this length. You can draw that on a piece of paper and then move it this way and draw a square. Then you cut out those squares, and you place the 4 by 4 square on the 5 by 5 square, and then you're going to have to cut the 3 by 3 square a little bit, but all of the 4 and the 3 squares will fit into the 5 square. And there you have sort of given some kind of concrete way to understand the Pythagorean theorem. Try this experiment with any length of the sides of a right triangle, and then generalize the formula. The fourth pitfall upon which I'd like to comment is that we need to differentiate between concepts and computations. Thinking back to Ms. Sayers' essay on the lost tools of learning, and remember how the grammar stage gives way to the dialectic or logic stage. But there's no clear and concise moment at which this happens for a student. Rather, it is a gradual and organic development which happens as the child matures. A computation is the action of a mathematical calculation. It is the first stage of the trivium. A concept is an abstract idea or general notion. The student is reasoning through. Don't let a student's limited ability in computations interfere with being exposed to new concepts. Many students struggle with the minutiae of computations. Long division, multiplying large numbers, and feeling the hair rising on your arms and your neck. These types of computations are absolutely necessary to getting correct solutions to a mathematical problem. Please don't misunderstand. That a student can accurately perform these operations is essential. An example here might help. I once tutored a boy who was in the 4th grade, schooled by his mother and father. His mom let me know that he was having trouble with adding and subtracting fractions. Upon meeting with the child, I realized he did not know his multiplication tables, which is a skill necessary for finding common multiples of numbers to obtain common denominators to add and subtract fractions. After a short conversation with his mother, I determined that she had been grilling him for over 2 years on his multiplication tables. But in fact, he was still unable to call up the math facts needed to proceed with fractions. Working with him a little bit, I realized that he understood the concept of fractions, and had I thought he did not, I would have spent time with him on making fractional equivalents with objects, which would help him to understand this concept, which challenges so many. While he was able to go forward with the new ideas, he was immobilized by his inability to make common denominators. So, I suggested that we give him a 12 by 12 multiplication table for him to use while he was doing his fractions. As a result, he was able to proceed with working with fractions. You all know what those are, the 12 across, 12 down, you fill in all products of the, yeah. Just making sure. He was able to use the chart, and that was essential for his progress. Without it, he would still be trying to learn the multiplication table, would probably be very bored, and eventually decide he hates math. You're undoubtedly wondering whether or not the boy was required to learn his multiplication facts. As a result of being able to use the chart, he would create one each time he needed to use it from his own memory. So the first thing he would do is make that chart. So then he could use it, and he had one to use when it was needed. He eventually did not need it anymore, and so he was quite successful, and he did not lose his love for mathematics. The next time you're shopping, hand your child a cheap 4-function calculator and have him check the unit prices on the peanut butter. There must be 15 different size peanut butter containers, from the single serving to the mega family size. Have him divide the price they determine the price per ounce. See if the tags on the shelves are correct. And in the meantime, the student is getting the idea of unit price while not getting bogged down in the long division. Of course, when he returns to the textbook another day and he is asked to determine the unit price, he will have to perform the division necessary, but having done so on a calculator, he knows what it is he has to do, divide. Another aspect of this pitfall of concepts and computations is illuminated when a student puts an incorrect final answer, but has a correct approach. To encourage a student to write out a reasoned solution, a student should receive some partial credit for this, unless it is a purely objective measurement, like multiple choice, or short answer, which should be used at times, but not all the time. When evaluating a student's work, it is important to follow how a student solves a problem as well as what his answer is. We should ask our children to write out the work they are doing so that we need not interview them each time we would like to know how they came about the solution. We must keep in mind that there are often numerous ways to come to a solution, while there is usually one correct answer, and that the final solution may appear in different forms. Often, a student makes a mistake or an assumption that is incorrect. By looking carefully at the student's work, we gain untold insight as to how a student is thinking about a concept. On numerous occasions, I have marveled at the different approaches taken by a student who is thinking completely correctly, yet not how I was thinking about a particular question. Once a student asked me why his mother marked a certain question wrong. It turned out that it was a rounding error. The boy was using 3.14159 for pi instead of 3.14. In a way, this was my fault because I had instructed him to use the slightly more accurate estimation of pi. But as a result, sometimes his answer would be different from what was in the answer booklet. Mom was unaware of this and was just marking them wrong, which was a bit deflating for the boy. It was something the mother had not considered when grading his work, and it was easily identified. The fifth pitfall isn't really a pitfall at all, more of an admonition about good habits of learners. Be organized, drill, review, and extend the problem. Helping a student to have what he needs in terms of definitions is essential to his mastery of the content and his ability to synthesize information. Keeping a notebook whose content is definitions with examples can be very helpful to a student whose memory needs regular prodding. Review all the time. One textbook, which is very popular among homeschool families, gives a new concept every day, some practice on that concept, and then has 30 review questions. This is an excellent way to keep those definitions current in the mind of the student. Then, when he is ready to make a reasoned approach, he has what he needs to do at his fingertips and possesses the facility to do so. And one must extend the problem. Go further than the basics and encourage divergent thinking. If you are in need of inspiration, online, one can find information and videos about mathematical concepts which are not routinely taught in a textbook or in a typical grade school curriculum, but are so interesting and fun, and students of all abilities and backgrounds can enjoy. One such blog that comes to mind is by a young woman named Vi Hart, a self-proclaimed recreational math musician. Vi has made, using stop-motion photography, videos which explore, among other things, Fibonacci series, and how these sequences are found in nature, and often offers insights as to why that might be, or how to fold paper into hexaflexagons, or even her singing pi gram. Seriously, she sings like 50 digits of pi to a song she made. That's pretty funny. Her name is Vi Hart. Yep. Definitely recommend it. She's young. She's like 23 maybe. Sorry. I personally find her videos riveting, and they are done by her own hand in the style of doodling. I think if I were back in the classroom, I would have my students watch these and draw the doodles. I highly encourage you all to take a look at her materials, or study the geometry of a baseball field. My final note is about the SAT exam. The SAT exam is a reasoning test. It is not a mathematics test to find out how much math the student knows. Although we do have SAT subject tests, which are relatively content-driven, and some colleges do require them. If you have a student starting the 9th grade, I encourage you to familiarize yourself with the subject test aspect of the SAT, since these sections may be taken any time and are often best taken, for example, after studying world history or biology, which may not take place in junior year. Meanwhile, the regular SAT exam has 3 parts: writing, critical reading, and mathematics. The level of math on the SAT is not very difficult, and to be sure, there are 8th graders who take it and do quite well. Rather, the math section of the SAT is a reasoning test, and a reasoning test in the language of mathematics. It challenges the student to think and reason in the vocabulary and symbols of math. Here is a sample SAT question. Find the sum of the smallest prime number and the greatest factor of 100. All just about definitions. Does anyone know what the smallest prime number is? No. Technically, it's not 1. A lot of people answer 1. By definition, it's 2. A prime number is a number that has exactly 2 factors, 1 and itself. Common mistake on the SAT is for people to use 1. Does anyone know what the greatest factor of 100 is? 100. A lot of people put 50. But 100 is actually the greatest factor of 100. So you add 2 and 100, and you get 102, you get the question right. Simple reasoning, simple definitions, being able to call those definitions up, simple vocabulary. If you're interested in exposing your child to the style of SAT exam questions, I urge you to do so by going to the collegeboard.org website and signing up for their question of the day, which delivers a question each day to the email you designate. It will give immediate feedback and will even tell you how everyone else who took the question did, which is how the SAT exam is scored by comparison to everyone else who took the test. Just a quick note on that. I don't know if you all know that, but when you take the SAT, your score is in comparison to everyone else who took that SAT, and they do it on a normal bell curve. So the average grade is assigned the value of 500, and going up 1 standard deviation and down 1 standard deviation is up to 600, down is 400. Two standard deviations up and down would be 700 and 300, and 3 standard deviations above and below the mean is 800 and 200. So the highest score is 800, the lowest score is 200. And if you want any more information about the normal curve, I'm happy to answer questions on it. To conclude, I offer the following thoughts about mathematics pardon me, by Proclus, who lived from 410 to 485. This, therefore, is mathematics. She reminds you of the invisible forms of the soul. She gives life to her own discoveries. She awakens the mind and purifies the intellect. She brings to light our intrinsic ideas. Thank you for your time.